you have a big screen, you can put two windows side by side. That helps, or else you would need to switch between the two. If you get stuck at any point, just let us know in the chat, and then we'll get you going again. Minutes. I'll give some demonstrations so you can get a feel of what you can do with quantum computing and how you can get started yourself. And that will also, along the way, demonstrate the strength of quantum computing and how it works. All right, so let's get started. If we move to the IBM Quantum Experience, you can also go to this page by just entering IBM Quantum Experience in your favorite search engine, and then it will come up with the appropriate link. If you look, so you have create an ID with your name on it, so that is what it says over here. Let's see what kind of interesting information is on this screen. Let's move to the cool stuff, literally the cool stuff, the very cool stuff below zero temperatures, and that is the hardware. So you see here on the right a list of backends, 10 backends, and that is a collection of hardware, and also there is one simulator. And that is, if you are just a, let's say, normal person, as I am, just anyone across the globe, well, that's the range of machines between 1 qubit. There is a 1 qubit machine, various machines with 5 qubits, and one machine with 15 qubits. And let's have a closer look at one of them. Let's click the IBM Q16 Melbourne. The Melbourne is just a name. It's not where this machine is located. It's just a name where IBM or a city where IBM has research teams. What do we see on this page? We see the topology of this 15 qubit machine. So we have qubits 0 up to and including 14. So all other qubits. So some have 3 links, and some have only 2 links, and there's one that only has 1 link. Right, I'll demonstrate later what you can do with the links between the qubits, but with those links you can have interactions between qubits. So in short, you can just manipulate those qubits individually, and I'll give some examples later on. And you can manipulate pairs of qubits, like the qubit 0 and the qubit 1. What you can see as well on this page are these very interesting couplers, and those are the error rates. You can these errors are determined through calibration, and the calibrations are done periodically. So, for instance, the qubit 0 has this light blue ring, which says that probably somewhere here, over here, that's the magnitude of the error rate, which means that about 1 in 1,000 single qubit operations might have an error. And yeah, that means that if you expect the outcome to be a 0, then the outcome might be a 1 in 1 of thousands of the times that you repeat this experiment. So the hardware is not ideal, and the effect is even stronger when you have multiple qubit operations, for instance the C0, and that I'll explain later as well. This is a 2-qubit operation between, for instance, qubit 0 and qubit 1, and then calculations, you can just go to the IBM Quantum Simulator, and what you see here as well is that there is no picture. It doesn't have a fixed topology, so you can have interactions between all the qubits as much as you like. So that's really the ideal quantum computer. No error rates and very high internet connectivity. Okay, so that's the hardware that's available to you. We have other hardware as well. We have 20 qubit machines. We have up to 53 qubit devices. But those are not available to the general public. Those are available to members of the IBM Quantum network. But still, with this set, you can do quite a lot of experiments, and you can this menu, you can view your results. You can run the circuit composer, which we will do later, as well as qiskit. We'll dive into that as well. But let's move to the resources first. And there you see 4 possibilities. Anything you want to know about managing your account and services, we'll skip that. Let's expand the circuit composer part. And what you see here is all kinds of guidance of how to work with the circuit composer, and I'll demonstrate the composer later. And what this does, if you start just at the beginning, you start with using the composer, you're going to perform step-by-step tutorials, learning how quantum computing works. And quite rapidly, this really goes into the more difficult stuff, up to phase estimation, for example, or short course algorithm. So this is a very interesting tutorial that you can go through using this environment, the composer environment. If you want to switch to programming quantum computers using qiskit, then you can go through this tutorial. There is a very nice book about learning how to work with qiskit and learn quantum computation as well. Let's open that. And this as well takes you through so this is also really recommended to go through this if you are really interested in quantum computation. So a lot of resources are available. Besides doing these kind of workbooks, going through this yourself step by step, there are also a lot of videos available. If you like watching YouTube videos and then putting things into practice, that's another way of doing this. Right, so those are the resources. Now let's get started ourselves. So let's go into this new circuit. And usually, of course, we would be in a classroom, and I would look into the room and see if people are stuck or whatever. So it's not possible, unfortunately, this time. But so if you have any problems, let us know through the chat. I'll just continue, and if there's a really a big problem, then Cor will step in. All right, what do we see here on this screen? We see this collection of lines, and what these lines represent are the qubits. So we have, in this case, a 5-qubit device, qubit 0 up to an. Anything. Just look at the theoretical measurement results, but it will all be stiff. So if we measure this, we get a string of 5 qubits, which are all 0. And the way these qubits are organized in this string is that the most significant qubit is the lowest one. So Q4 is the most significant qubit, and the top one is the least significant qubit. If we click on the left on this graph icon, and then in the drop-down box we select the outcome is always 0, 0, 0, 0, 0 in 100% of the cases. So that's, well, you could call this your first quantum circuit, but it's, I think, too easy to call it your first quantum circuit. So let's make it a little bit more difficult. For instance, how can you manipulate these qubits? And what I'll do is, on the left you see this settings wheel. You can increase or decrease the number of qubits yourself, and let's move to a single qubit. So you see one line here, you see another line here. Can be 0 or 1, and there can be a linear combination of 0 and 1, which I'll demonstrate later as well. Let's move back to do the measurement results, or probabilities on the left. Not the state factor, but measurement probabilities. And again we see a string which only contains 1 bit, and that is 0 100% of the time. Let's do a classical manipulation and drag the X gate onto this qubit line. What the X gate does is that it flips the qubit. So it changes the state from 0 into 1. An instantaneous calculation of what your circuit is doing to the qubits. If you really want to run this on hardware, first we would need to give this a name. So let's call it yeah. Right, typing skills, development community. Then I save this, and what I need to add before running this is I add a measurement gate. So what this does, it measures the state at this position, the state of the qubit. You can choose what kind of backend you want to run this on. You can run it on a simulator, or you can run this on any of the devices that are available to you. And there is a single qubit device as well. I'm not sure what the length of the queue was, so Let's get back to the opening screen and move to this single qubit device. That's the IBM Q Armand. It has 0 jobs, so that's well, we don't need to wait long. For instance, the orange is having a queue of 36 jobs. That might take some time. So let's try the IBM Q Armand. And the nice thing about this environment is you see these tab pages. Device, and because there are device errors also in this one, we select the number of shots. So we perform this simple experiment 1024 times and see what the result is. So let's run this, and what then happens is this is sent to this machine in the background. If I click on results, then you see that this job is running. And then let's move back to the hardware, because I forgot to, that was my job. There was one job in the queue. That's three. So I would expect this measurement to go wrong, or this, this to go wrong just a few times of this 1024. I did one single qubit operation, but that's not the only thing I did. I also did a measurement. Measurement errors are not given here, but the measurement errors are typically just a little bit bigger than the single qubit errors. So I expect well, about 10 times this going wrong. Now then, let's see. It's still running. Let's see if anything pops up. Created, completed. Right, it's completed now. So indeed, to the circuit, what we had was we perform an X operation on qubit 0. So we flipped this qubit and turned it from the 0 state into the 1 state, then did measurements. There is a intelligent transpiler that interprets or compiles, let's say, this circuit into something that is runnable on the hardware. That looks like the circuit on the right. So that's really executed on the machine, and then this is the result. So that's how it works. And with any circuit you create on the composer, you can run it in this way. Right, let's go back to the experiments and play around a little bit more. But I'll so this was a very easy circuit. Is there something quantum we can do, or maybe a little bit more classical? If we apply another X to this, what do you expect the result to be? Right, I hope you all have the answer, and that is that we turn this into a 0 again. So we have 0 here, we flip it, it becomes 1, we flip it again, it becomes 0 again. 100% of the time. So that's just classical operation. Now let's do something quantum. And let's apply the Hadamard gate, the H gate. And what this does is it puts the qubit into superposition. So a linear combination of 0 and 1 with the probability of having a 0 exactly the same. very determined state into something that is completely undetermined. It can be 0 or it can be 1, and we don't know until we measure. That's superposition, and that's really a quantum characteristic. There's no classical equivalent. Of course, you can flip a coin, and it is either heads or tails while it's up in the air, and even if you catch it and recover it, it's either heads or tails, and you just don't know. But it's really something different than having a quantum state. And I'll demonstrate why in a minute. Okay, now if we add quantum registers, if we go to, for instance, 5 qubits, and 00001. And remember, the top qubit is the least significant bit, and the lowest qubit, Q4, is the most significant bit. And the other bits, Q1, 2, 3, 4, are just 0, and they remain 0. Let's get rid of this one. Now, if we apply Hadamard gates to all of them, then you see an explosion of possible outcomes. 2 to the power of 5 results, each with the same probability of occurring. So with just and have all the states that are possible with just these 5 qubits. Those are 32 possible states. So 0000 up to and including 11111. Right? So that's maximum chaos, and this increases exponentially. You will probably or hopefully appreciate the power of this chaos later on in this session. Let's simplify things first again, and move to 2 qubits. Get rid of the quantum stuff and do something classical again. The classical gates, at least something that we can. This is the C0 gate, and what it does is it looks at the top qubit, Q0. If the top qubit is 0, then it does nothing to the second qubit, to the Q1. So if this one is 0, then the Q1, which is starting as 0, is unchanged, and the result is remains 0. Now, if the top qubit is 1, then what it does, it applies an X to the Q1. Just applying the gate X. Then at this point, at this stage, this one is 1, the lowest one is 0, and because the top one is 1, it will flip the lowest one, which becomes 1 as well. So both are 1 as a result of this simple circle. So indeed, the result is 1, 1, 100% of the time. Yeah, and if we would flip the lowest qubit first, and it starts off with 0, then because of the X, it becomes 1. So then the result is the result is 0, 1. So remember, the last one is the lowest one is the first one, the most significant bit. It starts with 0, it becomes 1, and it then gets flipped into 0 again. So the resulting state is 0, 1. All right, so this is just classical. Now, if we would have something quantum as the control qubit, so the top one, let's create maximum chaos on this first line. and we do it with the Hadamard gate. So what then happens, let's move this back, that just before it just starts calculating and applying this C0 gate as if it is a linear combination of 0 and 1. So what it does, half of the times it flips this second qubit, and half of the times it doesn't flip the second qubit. So that's very interesting. Let's see what happens. So here we have 0, 0. Then over here we have, for this Q0, we have a combination of 0 and 1. And of course Q1 is just 0, remains 0. And then depending on whether this one is 0, it doesn't flip. So then the result is 0, 0. And indeed, we see 0, 0 as one of the outcomes. If this is 1, then it flips the other one. So the result is 1, 1. Just as we saw in the previous what we see here is are two effects of that are really important in quantum computing. One is superposition, and the other one is entanglement. So entanglement means that if I know one of the two qubits, then I also know the state of the other one, because there are only two distinct outcomes here, 0, 0 and 1, 1. So if I measure the top of one and it is 0, then I immediately know that the other one is 0 as well. And the other way around. So if I measure this one, it's 0, then I know the top one is 0. And if I measure the top of one, it's 1 as well. And this is a very strange, non-classical state. Because, well, you can imagine if you put one of the qubits in a very rapidly traveling rocket and send it off somewhere into space, and I have two observers, and those start measuring qubits, but they don't know when they are measuring it from each other. They cannot signal, then you run into very hard problems to solve classically if you want to explain that there is a perfect correlation between. So this is one thing that puzzled people like Einstein very much. Yeah, all right. So there are some philosophical aspects behind this. So this is superposition and entanglement. Two very important things in quantum computing. All right, so what's the use of this? Now let's move into a practical example. Suppose I'm given a black box. And I'll create a circuit with 5 qubits. And this black box, I'll just put it between something really that has a function in the composer. So it gives the assignment or it tells the transpiler not to do any optimization across the left side of the barrier and the right side of the barrier. In this case, I just use it as a function of for the layout of the circuit, just to make it more clear. Let's create a black box, and what the black box does, black box because we know what is inside, but let's pretend this is a black box. The black box has an output, which is Q4, and it has 4 inputs, which are Q0, 1, 2, and 3. So this is the black box. Now somebody gives this black box to me and asks what is the relation between Q0, 1, 2, 3 on one hand and the output Q4 on the other hand. So in other words, if I change the top qubit, does it then influence the last qubit? Q0 doesn't influence the Q4. And if we look at the results, and you can consider this as a classical circuit for now. If I manipulate Q0, if I put an X over here, I turn it into 1, then the Q4 doesn't change. Q4 is the first one, right? The most significant bit. So we need to pay attention to those cases where Q4, which is the first one over here, changes into 1. So if I put an X here, it doesn't change, so Q0 doesn't influence Q4. If I drag it over here, 4 is changing. So then I see that Q1 influences Q4. If I drag it further to Q2, then again I see that there is an influence of Q2 on Q4. Q3 doesn't influence Q4, right? And we see it also from looking into the black box. Now, classically, if I'm given such a black box with 4 inputs and 1 output, then I would need to do 4 evaluations of this black box in order to see which bits influence Q4. Right? I need to drag this onto each individual line to see what is the relationship between the inputs and the outputs. If I do this on all four lines. So all 16 possibilities go into the black box at the same time and then have some result. Now, the result is that all 16 possibilities are the outcomes of this circuit. So that may not really make sense. But if we look into the results, then we can already see, maybe able to see some correlation. But again, here we have these 2 effects. We have superposition and we have entanglement. Something magical happens. We only get 2 possible outcomes. 0, 0, 0, 0, 0. At least 5 zeros. And we see another outcome which is 1, 0, 1, 1, 0. So if we execute this circuit, we have 50% possibility of finding just 0, a bunch of zeros, which doesn't make sense. But also 50% probability of finding 1, 0, 1, 1, 0. And the interesting thing is, of course, the first qubit, which is the most significant bit, which is Q4, is a 1, and that was what we are looking for as a result. And then Q3 is a 0, Q2 is a 1, Q1 is a 1, and Q0 is a 0. So this gives away what is, And this is pretty amazing because classically we need to apply 4 evaluations, one by one. And using quantum, we on average need to apply or need to run this or evaluate this circuit twice. We do a single shot, we may get 0000, or we also may even get lucky and find the result in the first shot, or else we would need to try again. But on average, in every 1 in 2 times, we would find the correct mask. And this is magical because if we increase the number of qubits and increase the size of the black box, then still we have this 50-50 probability. So classically this would grow as the amount of qubits grows, but in quantum computing you just need on average 2 evaluations to get the outcome. And that's pretty amazing, and that combines superposition, entanglement, and the last thing over here at the resulted. Alright, so that's the composer, and that is, yeah, let's say the power of quantum computing put into action in a very simple circuit. And I invite you to play around with the composer and go through some of the materials in the resources to gain more knowledge of how this all works. Yeah, let's check with Cor if there are any questions at this stage.
I think you have given a very clear overview, so no questions at the moment from the audience.
All right. Okay, good. Let's proceed then. Okay, so what else is here? On the left, there is this strange icon, which opens up the quantum code for this circuit. So change or whatever you want to adapt this circuit, you can also do it in this environment. If I put a 3 here, then it immediately changes the circuit. Of course, this is nice, but the functionality is limited. We can, of course, run this on hardware, we can run this on simulator, we can look at the state factor, we can look at the probabilities, all kinds of stuff for educational purposes to understand what you're doing. But if, for instance, you want to feed something in here which has a parameter, yeah, you can use some kind of parameters in this code. But if you want to post-process your results, if you want to pick up your results and then do calculations with those, and let's move to the environment, the qiskit notebooks. So what is qiskit? This is a software development kit for quantum. If you go to qiskit.org, then this opens up a website, and you can find a lot of information about qiskit. On this website, there are videos on YouTube. This links to the Quantum Experience that we have worked on previously. It tells you a lot about qiskit. So there are 4 modules in qiskit. We'll look at Terra and Aqua. And Terra is the, let's say, the basics. Terra is the module which allows you to work with circuits, as we've done in the composer. And what qiskit does, it allows you to use those later on. So you can do Python programming and use the methods that are available in classes that are available in the qiskit library to work with quantum. And you see an example on the right here. You do an import of some things in qiskit. You define a quantum circuit with 2 qubits and 2 classical bits. You apply Hadamard gate to the qubit 0. You apply the C0 between Q0 and Q1, and you do a measurement from Q. Runs a simple circuit that creates entanglement. Yeah, you can of course adapt the code to see what happens. You can copy and paste this into a qiskit or a Python notebook. Now the interesting thing is you can do this in the same environment as well. And there are a lot of tutorials already available to you in this environment. So the qiskit tutorials on the right here, you can just go to start here, and then it opens up this notebook. At least it should open up. Take some time. On. But something is happening. Very good. Right, here we are. So these notebooks contain text in a nice markup. So these explain a lot of things, and they might also contain code. Let's move to an example, getting started with qiskit. So let's see how this works. So again, we see some text, and then we see a cell with code, and this cell contains Python code. This is Python what you're looking at, and then you can execute the code by clicking this twisty. So it includes some libraries. Over here we can define a quantum circuit with 3 qubits. There's some explanation. We apply a Hadamard gate to the first qubit, qubit 0. We apply a C0 and we apply another C0. And then we can draw the circuit. And this is the result. So Hadamard gate and 2 C0s. It on the back end and collect the results, and then what we see here are the results, not the counts in this case, but the state vector that is the result of applying this circuit. Let's skip that. I'll leave it to you. But here we go really into measuring the results of this circuit, and here are the results. So 0, 0, 0 and 1, 1, 1, each approximately 50% of the time. So here we have again created entanglement, but then between 3 qubits instead of 2. you may be able to do some pre-processing, or post-processing on the results. You can, of course, manipulate your program. So this is the lowest level on which you can work with. Well, no, it's not the lowest level. You can go one level deeper, lower, really close to the hardware. You can also work with the pulses that influence the qubits. You can really manipulate those qubits on the lowest level with electromagnetic waves. And then one level higher is applying these kind of gates. For instance, you may go to a little bit more complex circuits with 5 qubits. And here you see some code, a bit more complex circuit, executing 1024 times, and then looking at the result. Right, so you can do these kind of experiments yourself, and this is creating a circuit, running the circuit, and looking at the results. So that's in short qiskit Terra. Complexity, like I've done here. This is, of course, this a circuit, but this is also a algorithm. And an algorithm is just a circuit that has a specific purpose of solving some kind of a puzzle. And this is the phase estimation algorithm that you're looking at over here. So then we are already moving up in the software stack. We are moving from basic circuits to algorithms. So let's move to Aqua, because Aqua is the module that contains algorithms and domain level application. So algorithms like the phase estimation algorithm that you see, but also the domain level application. What I mean with domain applications, well, you saw maybe if you participated in last week's session, you saw that Core mentioned that quantum computing has promising application areas, which include chemistry, optimization, and AI. And Aqua already contains modules that you can use for those domains. For instance, over here you see a search algorithm put into practice. But I'll give you some more examples. To get you going, of course, qiskit textbook, which I recommend. You can also go directly to the API references. Let's look at Aqua, what's inside Aqua. So here you see that Aqua contains algorithms. Yeah, so the algorithms like amplitude estimator. You see the QSVM. People who are into AI may recognize the support vector machine acronym, SVM, and there is a quantum equivalent as well. You also see all kinds of solvers, eigensolver, linear solver. The variational quantum eigensolver, which is used in chemistry and optimization as well, and of course the quantum phase estimation that I showed previously. So these are ready to use algorithms so let's click on one of them. So the QSVM, for instance. And if you click on that one, you can see some explanation. What does it do? What are the parameters? And what is the result? This one. If you are looking for anything quantum in this, so where are the number of qubits, what does the circuit look like, all kinds of stuff on the lower level of the stack, then those are made invisible, let's say. So those are under the hood of this QSVM algorithm. So if you are into AI, then you may recognize some of these parameters. So that makes this library very powerful. And I'll show you a demonstration later. Same for chemistry. So the BQE algorithm. If you are into this, then you may recognize some of the attributes, for instance, and methods. But let's put this into practice to make this more visible. Let's get rid of some of the tabs. And in the One Start Here tutorial, you can go through all these tutorials. In this session, but yeah, moving to qiskit Aqua, so using some of the algorithms that are in Aqua, and then moving further up in the stack to applying all this into really business domains. So, for instance, for machine learning, let's look at quantum machine learning. Over here you see the Quantum SVM for classification. And that's a notebook. And what it does, and you can go through this later yourself, it does some imports. Just generates data that is plotted over here. And you see the blue dots and the red dots. And then the challenge is for this algorithm to learn what are the blue dots and what are the red dots, and then later on, if we apply test data, basically the same data, can it recognize whether it's a red dot or a blue dot? And so this is machine learning. So we have a small data set over here, and then with this small piece of code, which is really small and doesn't contain any just AI stuff, we are able to train the algorithm with the data and also do the test. And here we see a success ratio of 1, which means that this algorithm has all the results correct. So if you compare point 1, it should be an A, and it is an A. It should be an A, and it is an A, etc. So it's correct 100% of the time. And for those of you who are into AI, here's the kernel matrix. So this is already putting quantum into practice. Just another example, for instance, in chemistry, and there are also applications in finance and in other kinds of automation. But let's move to chemistry. And this is another notebook. We'll go to chemistry using PQE. And what you can do with this notebook is that you can do calculations on hydrogen molecules. So here's a bit of theoretical background, which I will skip for the moment. And then move to the code. We have some code specifying what kind of molecule we are looking at. So in this case, we are looking at the hydrogen molecule. We are preparing the PQE algorithm with some parameters. And then over here, we are running the algorithm to find the energy state of the molecule as a function of the interatomic distance. Well, at least that's what we're doing later on in this tutorial. And this is the result. The nice thing about qiskit, it contains also some classical algorithms, so you can do comparison between the classical result, which is more exact in this state, and the quantum result. And you see some gap between the two, but at least they are quite close. What you can do as well is if you change the interatomic distance between the two atoms, you can calculate the energy level of the molecule. You see that it's some minimum, so this is the preferred state of the hydrogen molecule. Hydrogen is very simple. It contains of just two nuclei and 2 electrons. So those are 4. Taking into account all the interactions between those particles. And those are 4 in this case, so that's quite simple. But if we move to more complex, molecules, then that's slack. Then you may appreciate that the complexity rises very rapidly. If we increase the number of electrons or interactions that we need to take into account, really explodes. And well, from what I showed in the beginning of this session, is that this is something that also happens when applying quantum computing. If you increase the number of qubits, then the number of possible states that you can do calculations with explodes as well. So this is very handy for these kind of problems where there is an exponential growth in the complexity of your problem. Alright, so already very powerful. You can do calculations on simple molecules. Available in qiskit. And basically what we've done is we've traveled from the hardware through the composer on the circuit level, the gates, quantum gates, and then moved up to qiskits, to algorithms, and then up to the domain level application. So there's a full stack, software and hardware stack available for you to play around with. So that basically covers what I wanted to discuss this afternoon. I'm not sure if there are any questions at this stage, Cor.
Yeah, an interesting question in talking about the backends. So so to say, what do you have to do in Python in your notebooks?
Okay, yeah, right. So let's look at the the getting started with the qiskit tutorial that we opened previously. So let's see where it is. Yeah, this is simulator. Right. If you have logged into this environment, and right, yeah, no, let's stay over here. You need to do some preparation in order to be able to work with the backend, and that's explained over here. You need to load your account into this environment. You only need to do it once, and then it's all set. And then there are some pretty powerful commands that you can use to check what kind of backends are available to you. You can even see the length of the queue if you change some of the parameters of this code. Execute this piece of code. Backend is equal to provide a get backend IBM Q SX, for instance, if you want to use the IBM Q SX. And then you execute your job on this backend. So that's how easy it is. So instead of using the simulator, you just select this other kind of backend. And there are other commands available to you to monitor how your job is doing. So if it is still being executed, and then you can have your Python code wait for the result. Once the result comes in. Difference between working with the simulator and the hardware. Well, the only difference is that you may need to wait for the result to become available. So you need to include some additional statements in your program to wait for the results before you can plot it. Not sure if that went into your or fully covered your question, Cor.
So to quote the person who asked is excellent. Thank you very much. So it does.
All right. Anything else? I'm not sure how many participants we have, or if we can open the call for.
I think so. Yes,
voice.
we can. Yeah. Yeah.
So you can unmute yourself if you want to, instead of using the chat. And don't be shy, because there are no stupid questions in quantum computing. This stuff may seem obvious, but once you dive into it, the more you dive into it, the less obvious it becomes. So don't be afraid to ask any question.
Hi, I've got a quick question. It's really, you know, I see the potential in quantum technology, but in the company I work, that you know, quantum is something that's really coming. There's a lot of developments. How do I, you know, persuade these folks with practical applications? To start using quantum technology.
Right. Yeah. Most of the stuff that I showed you is focused on how to work with quantum computing, not on how to apply it in your organization or in your business. But there are collections of use cases available, and I will just go through to a
very basic, starter circuits, just to show some of the basics of quantum computing, like entanglement and superposition and interference, these kinds of things, right? But really, some of the beefier circuits that will be interesting in a commercial environment for optimization, for machine learning, these kinds of things.
Right. Yes. Yeah. Yeah, so looking at the business application, there's this article on quantumcomputingreport.com. If you do a search in this environment on use cases, you just type use cases over here.
Mm-hmm.
Or later I'll put this in the chat, this link. Then you see a list of application areas and use cases. I think interesting picture is over here. Here you see the same use cases organized by horizon, and there are 3 horizons. And the first one is where the point of what we call quantum advantage is expected to take place within a few years. So could be 2 years, could be 5 years, but at least the foreseeable future. So what does it mean, quantum advantage? It means that you can do things with quantum computing technology as a basis that you cannot do with in these use case areas. Look at, for instance, quantum chemistry. You can do modeling of molecules that are too complex to be modeled in a classical environment. The same for other kinds of use cases over here. So, vehicle routing, network optimization. We expect that within 5 years in these use cases, you will be able to do things with quantum computing that you are not able to do with classical. The computer on Earth cannot do the things that you are able to do on the quantum hardware that will be available. Hardware and software, by the way, that will be available in the next few years. So this may trigger or persuade the people in your organization, and well, the horizon point, so the point in time where quantum advantage will take place, is not the only thing you need to address in your organization. And another thing is what amount of time does it take for us as an organization to get ready for quantum advantage? Because you need skills, you need access to hardware, you need a team, or there's an impact on your business processes. So there's a lot of things that you need to do before you can get ready yourself and take advantage of this quantum advantage. So then if you have the assessment of how much time your organization needs in order to get ready, and you have an assessment of when quantum advantage will take place, then you need to know when to start your quantum journey.
If I look at this kind of horizon roadmap or this diagram, I work in a manufacturing company, and a lot of our use cases fall into these buckets in terms of optimization. Very very low level simulations of materials. So that would be very interesting to do. Would it be possible to have follow-ups with IBM?
Yes,
to
sure.
see if
Yes.
something is possible.
Yeah, definitely. Yeah. You can reach out to myself or to Core, or maybe you already have channels within IBM. But if you reach out to either of us two, then we would be happy to discuss the need.
Okay, that'd be great. Yeah.
Yeah.
By the way, my name's Milan. I think we're connected on LinkedIn.
I remember.
Yeah.
Okay, thanks. Yeah.
Okay.
Okay. Another question on the chat is then talking about, okay, you have TensorFlow Quantum and you have an IBM Qubit, so qiskit. Can you talk a little bit about the differences?
Right. Yes. Not at this stage. No. Sorry. Maybe you, Cor, can touch on that. I'm not sure.
Okay. Then a very short version then. So what you see in the TensorFlow Quantum is primarily focused, I think, on machine learning. And what you see then from a qiskit perspective, that's more kind of full stack approach. So Armand talked a little bit about the four modules, specific focusing on Terra and on Aqua. For instance, if you take a look at Aqua itself, there's also a couple of specific topics in it, not only machine learning and AI, but also talking about chemistry, around or did it answer the question just put on the chat? I think yeah. Okay, so that's the main difference. That's broader than just machine learning. So, any other questions? You can ask Armand the question.
I have another question. I've logged into qiskit and also onto the IBM Quantum Experience, and I played around a little bit. If I want to start using that commercially, what are the options?
I think if we get in touch and talk about quantum computing and application areas and the IBM IBM Quantum Network that we have for organizations.
It's not really. It's not what I think. I mean, when in a couple of months, let's look at what you did.
Sorry, I think we have.
Well, on that meeting, I actually asked that sometimes because of the security,
this is
that sometimes there is something needed urgently, and I got some hand-waving answer that I didn't understand.
Maybe you can mute it.
How it comes? Basically, I even give the Heartbleed example, and suddenly.
Right, that's better. Yes. So I think when we get in touch and we talk about quantum and the application areas, we can also talk about the IBM Quantum Network, and that is there for organizations to reach the point of quantum advantage.
Okay,
so there are possibilities of collaboration and, for instance, access to more advanced hardware, have a priority in the queue, and also access to knowledge and those kind of things.
Okay. I was just kind of curious, how expensive it would be compared to existing cloud services. So I do a lot of stuff in the cloud with a number of different providers. So I was also, just in the back of my mind, I was wondering how expensive the service would be. But from an organizational perspective, we are interested as well, so I can pursue it via that route.
Yeah. Quantum computing typically is offered through the cloud, so this is not a machine that would be put on premises. It's just too expensive, and yeah, it's not necessary. It's fully accessible through the cloud, so we maintain those in a quantum compute center, and you can have access through the cloud.
Okay. Well, thanks for that.
Hi, Armand. Hello.
Yep. Yes, we hear you.
Hi, it's Robert Coogan. How you doing? Great. Can you hear me?
Yeah. Yes, sure. Yeah, you go ahead, please. Thanks.
Thanks for doing this. What I'd like to ask is, and I don't know. I apologize if I missed it, but is there what commercial applications are currently being used? Like just a couple of examples. Is that possible? Like it's just, are there other commercial applications being developed being used right now?
Well, being used, there's no commercial advantage now for quantum computing. So the use cases that you can apply are just simply too simple, and you can.
Okay. Are they on par?
Well, yeah, we expect for the use case in Horizon 1 to reach this moment where quantum computing will have better possibilities than possible within a few years. Yeah, so at the moment, the best way forward, or no, well, not forward, but if you have a problem, you should solve it classically. That's the way at the moment. But in a few years, that will change.
Okay, yeah, we're basically just trying to be ahead of the curve a little bit here. So, and that's internally some of the applications. Yeah, some of the applications we were wondering, our team was wondering if we spent some time, kind of building. That's like, so that way at least it's. But if it was operating on par, we would have something to be able to compare it to, right?
Now, for the simpler problems like the hydrogen molecule or the simple data set in machine learning or traveling salesman problem with just a few cities, you can do comparison between classical and quantum. You can do calculations on the problem with quantum computing techniques as well. So you can do a comparison. And the nice thing is that you can gain experience, and you can easily scale up your problem once you have all your code in place. You can even create your code based on a problem that is impossible to calculate, and just put your code on.
Pattern recognition or identification within images, basically is what we're looking at doing. So we've been doing some machine learning with that.
Oh, okay, that's interesting. Yes, yeah, great.
Okay, I'll reach out to you later.
Okay, thank you.
Thanks. Thank you.
All right, any other questions, maybe? If there are any questions after the session, anything that pops up in your mind, whatever problem or anything, don't hesitate to reach out. We are happy to help. Okay, Hans, maybe back to you. Or Cor,
Yes.
anything to add?
No, I think
Armand?
Yeah, in my case, I only have 3 slides, which are not very meaningful. And
Maybe
of course,
you can
slides.
Maybe you can add a slide with some links to the documents you showed, or something like that.
Yeah. Yes, that's fine. Yeah, we can share that.
And then I try to share them with all the participants of this meetup, and also from last week. So thank you, and hopefully we will see each other again with some other sessions around this topic and maybe other topics. So keep an eye on our meetup page. We host several sessions a week, and there might be one.
Thank you very much, everyone.